I'm gonna close my video to save some Wi-Fi resources to make sure if this is okay for you. All right, so okay, let's get started. Okay, so last time we talked about the maximum likelihood estimation, and we use this method. We apply this method to the F2 design, right? So, but the problem is like because F2 design is a little bit more complicated than the backcross design. So, so ideally, we can see all the numbers of individuals in all 16 cells, right, in that table. Do you still remember, like this? So, but in reality, this is not true. But last time, by assuming that we know everything occurring in each of these 16 cells, we know exactly the numbers that we can easily construct a log likelihood function, and we can use the strategy described in the MLE, right? We do the first derivative and the second derivative, and we can easily get this MLE to estimate the R, right? And we can also easily get the variance of this estimation. So that's what we have learned last time. And we also compare these two designs here, the backcross versus the F2. If we have complete data for F2, if we can observe each numbers in each of 16 cells, then we can compare these two designs. So the conclusion is based on the variance here, we can make a conclusion that F2 design is more efficient than the backcross design because so based on the same number of the progeny, so the same sample size, we can get better estimation, or we can get a smaller estimation error for the R hat. So any questions?
So the NR is also the non-parental number of the...
Yes, the big, could you say that again? Are you asking about the big N?
The NR.
The NR? Oh,
yeah,
you mean
so,
here?
Yeah, the NR is also the non-parental progeny.
That's right.
Number.
That's right. Because in this equations, so the N is the same, the total number of the progeny, but the NR is not identical, is not the same for these two design. So even you have the same big N, right? Starting point as, so even you have the same sample size, big N, but when you use different design, you may end up with different numbers of the NR. So that's why. So for simplicity, I just use NR, but probably I need to use NR prime here. Those two are different. But here we're talking about the same sample size. Big N is the same. Is that clear?
So it's only the NR number is different.
That's
Maybe
right.
The NR number in F2 is smaller than the BC design.
Yeah, that's right. That's right.
But the meaning is the same. Like
yeah, the meaning is the same. Yes, very good. This is a very good. Sorry, kind of like lost my voice. Sorry. Yes, exactly. Here, if you compare these two designs, the big N is the same. The meaning and the number is the same, and the R hat is the same because the recombination should be the same. The only thing is the Rn, the Nr, sorry, the Nr represented the number of the progeny carrying the recombinants, right? Yeah, so the meaning for these two Nr is the same, but in reality, the numbers, the realized numbers in these two formulas are different. Okay. Yeah, very good question. All right, now let's stop imagination. So let's come back to reality. So in reality, we do not see all the 16 numbers, right? In the south, in this tables. What we can see is here. So if we cannot, so if we can only genotype the two loci for each progeny, and if we cannot get the haplotype information for these two loci, then what we can really see is this, 9 categories, okay? Instead of 16 cells, we can only see 9 categories, because if you look at here, this category represent, oh, let me remove this, sorry. This is a little bit messy. So, okay. All right, so please look at here. So if you look at this category, actually this category is a combination of 4 cells. 4 cells from this 4x4 table. Is that right? So in this table, the 5th category actually is a combination of these 4 cells. This diagonal, oh, no, sorry. Jeez, what did I do? Sorry about this. This is terrible. Okay, my apology. So this category actually is the combination of these 4. 1, 2, 3, and 4, right? And if you look at here, so what is here? This actually, so if we can successfully get the haplotype information about this two loci in this progeny, so if we can differentiate this 4, so actually this one and this one represent the parental type, right? So there's no crossing over occurring in any of these 2 alleles, two gametes, right? However, if you look at this 2, let me put a plus sign here. Oh, gee. Okay, how about this 2? These 2 represent the 2 gametes. Both 2 gametes have a crossing over between A and B. Is that right? So okay, so in this reality, so we cannot differentiate the progeny within this category. So that's the problem. So even we can construct a likelihood function like what we did before, right? But because of this confounding, because of that category, so 2 types like parental type and the double crossing over type are confounded by each other in the category number 5, right? So you cannot easily derive a closed form for the solution of the maximum likelihood estimation. So if you do the first derivative and the second derivative for this log likelihood function of R, so it's not easy for us to get a closed form of the solution. So is that clear? Any questions? So this is because, can you hear me?
Yes, I can.
Oh, okay, good.
We're
so scary.
We're at it. So so all four of those values, because the log likelihood function is we're not summing all those values, are we?
Yeah, we will sum up all these values because
Okay.
look at here. So yeah, this is a good point. In this case, compared to the previous one, right? The previous one, we sum up all the numbers for 16 subs. That's why in the previous case, this number should be 16. We have full information, complete information for 16 cells. But now we only have 9 cells, 9 categories, because some cells in the previous 16 cells are combined or are confounded by each other, merged together to form this nine categories. So this is so-called the incomplete data, because some data you cannot get the full information. Is that clear?
Got it.
Yeah, okay. So, okay, so this is a problem. So with this, so we call this incomplete data problem. So with the incomplete information or data, it's not easy for us to use the regular MLE method because it's very hard to derive a very nice closed form of the solution of MLE. So what we can do is we can use some like numerical method. For example, oops, okay, here. So we can use, for example, Newton-Raphson method to help us to get the solution instead of using the regular MLE, the very nice MLE. This theorem is kind of very complicated. So I don't want to spend too much time on this. I'm gonna describe this, but not too much time. And this is not required for the final exam. So just for your benefit, I'm gonna introduce this method. So if you want to look into the details of this method, so you can go to the page 20 in the text. So basically, what we do in the Newton-Raphson method is we can express the first derivative of the R in terms of the likelihood function by using a Taylor series expansion. And the Taylor series expansion, actually, we use this method to express the first derivative of R using this expansion based on the value of R, based on the, how do you say that? So based on a value which is very close to this one. So if R is very close to R0, which means R0 is in the neighborhood of this R, so then we can use this Taylor series expansion to express R using the R0. Okay, so if this is good, actually for this expansion, there are a lot of more higher order of the terms here, higher order, 2 plus 3 or something like this. But because as the order goes up, so this terms, the value of this term becomes very small. So we can ignore those terms. So then we just use this simplified form here to express the first derivative of R using the neighborhood value of R0. Okay, now, based on this, we can express R equals to this, right? R0, which is very close to R. And now, this is the core function here, because we can, if we have a R value, realized value for R at time t, then we can update this R value using this equation. So for example, right now it's the time t, we have a realized value for R, then we can use this equation to help us to update the R value for the next time point, t plus 1.
Pardon me.
Yes, go ahead.
What is, can you clarify what R naught is for 1 second?
Okay, sure, no problem. Let me remove all this first. And Okay, can you hear me?
Yep.
Okay. So basically what we want to do here is, so just like the maximum likelihood estimation, we do the first derivative of R. Is that correct?
Yep.
Okay, but we're using a different way. So what we do is like, okay, so for example, let's say this is the likelihood function. Do you still remember this?
Yes.
Okay. Let's say this is R, right? So we want to do the best guess for R to maximize this likelihood function, right?
Yep.
Okay. Now, so since we want to get the first derivative of SR, so we can treat this small region as a linear function, can we?
Yes.
So this is the R0, the label R0 here. This is the so-called the label in the neighborhood of R. So it is a R which is very close to the real R.
Gotcha.
Yeah. So, or in the other way, so right now, so at time t, at time 0, we have a realized value for R, which is R0, and how we can use this to express the next time, how we can use this R0, the value of R0, to express the realized value for R in the next time point. So the t plus 1. Is that clear?
Got it.
Okay, so this is how we do this. So suppose at time t, we have R0, then we can use this function, the Taylor series expansion, to express the SR, the first derivative of R for the next time point. Okay, now this is a beautiful feature. So since we can express the next time point R value using the current value for the R, so so by doing this, we can develop some algorithm called the iterative or iterative algorithm to help us to find the best solution for R. Is that clear? Is that clear?
Yep.
Oh, okay, good. All right. So for example, so once this algorithm is set up, so what we need to do is to give an initial value for R0. So we can, because for example, in our case, we know R must be a value in between 0 and 0.5. Is that correct? So we can give the initial value to R any value in between these two. So for example, 0.2. So we give R 0 equals to 0.2, and we start the iterative algorithm. So for example, this will go like this. So finally, this algorithm will converge at some point. So don't look at these values because this is not a good example because R should not be that big. So suppose like this is like 0.25. Okay, if you give an initial value to the R0, so if you let the iterative algorithm to go for a long time, so it can converge to some point, and this is the best estimation. When this algorithm converge, this will give you the best estimation for R. Is that clear? Any questions? Very good. Thumb up, good, thank you. All right. Now, so once the algorithm converge, so you can get the best estimation, and also you can use the same strategy, use the Fisher's strategy to get the variance of this estimation. Then you get the standard error and you can do the hypothesis testing, right? Is that clear? Okay, very good. All right, so here, so let's continue. For example, so in our 9 category example, so this is the first derivative. If you want to do the mathematics. So this is the first derivative and the second derivative, because it is too complicated. So I just write the first term here, and there are a lot of other terms here. Okay, so it's very complicated. So so in this case, we would rather not to use the MLE because it will not give you a very nice closed form. However, so once you calculate using the features information strategy to calculate the variance of this R hat, so this is the form you can use in this case. Okay, let's see the difference between this and the variance we calculated when we can see the complete information from the 16 cell problems. Okay, all right. So do you still remember if we can see everything in those 16 cells? So this is the variance we can get for the estimation of R. Is that correct? All right. But in this case, if we do not see all the 16 cells, we can only see 9 cells, 9 categories. So this is what we can get. So from here to here, because we ignore these two parts, because the R is a very small number, the R square should be very close to 0. So that's why we can ignore this part. So this is approximately equals to this, right? Okay, now if you just expand this, so it will become this. And it's C. C equals to this part. So this is C. All right. So this is the same with this, right? Am I right? And the C, so look at here, because R is a number in between 0 and 0.5. So which means this value, the 3 times R should be greater than 2 times R, right? And 1 minus that means like this thing should be bigger. The denominator is bigger than the numerator. So, no, sorry. So the numerator is bigger than the denominator, right? The numerator is bigger than denominator. Then this C is greater than 1. Do you agree? The C value should be greater than 1. So just give an example. So let's say R hat equals to 0.1. So the numerator should be 0.8, but the denominator is 0.7. So this ratio should be greater than 1, right? So which means, so if you deal with the incomplete data problem, 9 categories, so you get a larger estimation of the R estimation, R hat. Is that right? Is that right?
Didn't quite catch the last part.
Oh, okay. Let me remove this. So yeah, this is tricky, but yeah, but it is very important. Let's do this again. Okay, so this variance is equal to this. So this represents what? This value represents the estimation error for dealing with the incomplete data problem, where we only observed the 9 categories. Is that correct?
Yes.
Okay. Now this is from previous case. So this is the variance or the estimation error for dealing with the complete data sets where we can observe the whole 16 cells. Is that correct?
Mm-hmm.
Mm-hmm. Okay, look at here. So this part is actually identical with this, right? The only difference is the coefficient here. There's a C. So let's see what C would be. So C equals to this, right? Is that correct?
Mm-hmm.
So please tell me. So tell me something about C. Do you think C is greater than 1 or less than 1? Because R is a value less than 0.5, right? So let's give an example. So if R hat equals to 0.1, what is the value for the numerator? That's 0.8, right?
Yes.
And what is here? That's 0.7, right? So this ratio should be greater than 1. Do you agree?
Yeah. Yes.
And the whole thing should be greater. The whole thing should be greater than this. Do you agree?
Yes.
So
Yes.
what is that? What does that mean? That means like uncertainty increased. if we see the complete data, the 16 cells, we can get better estimation for R hat, right? But if we lose some information, if we can only see 9 categories, that means we have some information being lost. Then in this case, when we do the calculation or estimation for R, so we're gonna increase our uncertainty. Do we?
Which means the variance calculated by the C is greater than the
Yes, the complete case, the 16.
complete. Yes.
Yeah, the 16 means like complete case. We can see everything. But for the incomplete case, we can only see part of the data, 9 categories, because some small categories, subcategories are confounded by each other, right? So we lost some information, then that's the cost. We have to pay for that. Where do we pay for that? We pay for that by increasing the uncertainty of the estimation. So the variance of the estimate should be larger. Does that make sense? So yeah, I could ask you a question in the final, so pay attention. So I may ask you, okay, so yeah, please compare the complete case and the incomplete case. So what's the difference? So this is a major difference, right? Because when you deal with the incomplete data, you lost some information, and that's the cost. And you have to pay for that, and where. So when you get the estimation, you will get an estimation with less certainty. The variance of the estimation should be larger. Does that make sense? Okay, good. All right, so this is for the Newton-Raphson method. And move this window away. What the? Oops. Can you see here, the little window says, please move these windows away from, I don't know what does that mean. Okay, but anyhow, it doesn't matter. Oops, let me, oh, jeez. Okay. Oops. Okay, so, oh, what is this? Okay. Can you see my window? So what does that mean? Please move this window away from, what is that?
I think it's when, I just Googled it too. What does
Oh,
that
thank
mean
you.
for Zoom? But it says
Appreciate
that when someone opens up a different program,
Huh.
for some reason, if there's an incompatibility with Zoom, Zoom will flash that up.
Okay. But actually, so.
Yeah, and I'm not, the solutions to get rid of it, people said restart the computer, but I don't think that's that's a little disruptive.
Let's ignore this. So I don't think this will be too bothering us, right? Okay. Yeah, sorry about, oh, geez. So maybe I stop sharing first and then I do this again. Let's see. Okay, maybe this is better. Let's see if it is better. Okay. I think, yeah, Zoom has a lot of room to improve, right? Based on my experience. Oh, better. Okay. Let's continue. All right. Okay, so this is for the Newton-Raphson method, and so it's very nice when we deal with the incomplete data problem. But also there's a problem, a major problem for this method, because so when we calculate the second derivative of R and we try to use the inverse of that thing to calculate the information, features information, sometimes I'm gonna tell you in what situation this will occur. So sometimes when we calculate the inverse of this thing will be easily overflowed what does that mean? That means like when the R, the HR, the second derivative is getting very small, close to 0. So the inverse of a 0 should be a infinity. It is a very extremely large, right? Infinity. So that will cause the overflow. So this is the problem for this method. So to improve this, so Fisher developed another better algorithm called the Fisher scoring method. So this is the Newton-Raphson, and this is the Fisher scoring method. The only difference is here. So here Fisher uses expectation of the thing. So this thing, and this can in most of the cases, this can solve this problem over a flowing problem, and the rest of the thing are identical. So this is how we calculate the information for this, and this is the Fisher scoring method. All right, this is the only difference between these two methods. And so this is how we use the matrix notation to do this. So this is not required, just for your information, because when you write the publication or derive your own formulas, so it's better to use a professional way to present it. So this is how we can use the matrix matrix form to express the calculation of the estimation of R and the variance of the R using the Fisher scoring method. All right, so as I mentioned, the Newton-Raphson and the Fisher scoring, they are very close to each other if we're dealing with the situation when R is not close to 0 or 0.5. Those two represent two extreme cases, right? The 0 means there's no recombination at all. It means like the two loci are very close to each other. 0.5 means like either these two loci are unlinked, or even they are located on the same chromosome, but they are far removed from each other. So in that case, the R, the recombination frequency, is close to 0.5. So in these two extreme cases, the Newton-Raphson is not that good because of the overflowing problem. But the Fisher scoring method can solve this problem, can better solve this problem. So this is the improvement by the Fisher scoring. Any questions before we move forward? All right. Okay, so I think this is the last thing I'm gonna introduce for this chapter. So this is another very, very useful method. I bet many of you have already heard about this method, EM algorithm, the expectation and the maximization algorithm. So this is also just like the Newton-Raphson or the Fisher scoring method. This is also a iterative algorithm, but in this algorithm there are two steps. One is called the expectation step, and the other one is the maximization step. And these two steps are alternated by each other. So the program also need to run a lot of times until it converges to some point. And then when the program converges, you can get your solution for R hat. And then you can also get the variance of that estimation. Then you can do your hypothesis test. All right, so what is this table? Can anyone tell me? This is F2 design, right? Of course. And how many cells do you see from this table? 16. So this is the complete data problem, right? All right. But in reality, we only see 9 categories. So why is that? Because if you look very close, if you look closely at this table, you're gonna see the same color represent the subcategories that are confounded by each other. So this two yellow thing, so if you just look at the genotype of this group, so they are identical, right? If you do not have the haplotype information, so just look at the genotype of these two loci within these two categories, they are identical. So that's why, yeah, you do not see 16 categories. So in reality, we only see the 9 categories here. So so instead of looking at the gametes, if you look at the genotype at each loci, so for example, if you look at the A loci, locus A, so there are 3 possible genotypes from this F2 design, right? And the same, if you look at the second locus, the B locus, also you're gonna get 3 genotypes for this locus. And these 9 categories represent the 9 possible genotypes you're gonna observe based on these 2 loci. So this is how we can link these 2 tables, right? Is that clear? Yeah.
That's how you can link the 2 tables, but what is?
Yeah, this actually the same data. So we're talking about the same data from a F2 design. Is that correct? So if you do F2 design experiment, you're gonna generate a lot of progeny. Let's say 1,000 progeny, right? And if you look, so if you genotype each of the individual based on these 2 loci, you're gonna. So suppose you can get the haplotype information, then you can generate a table like this. Do you? Can you?
Yes.
Okay. But in reality, if you cannot get the haplotype data, if you can only see the genotypes for these 2 loci in each of the progeny, so in reality, you can only generate a table like this using the same data.
But what does that have to do with the expectation maximization algorithm?
Yeah, I'm gonna talk about this.
Okay. Okay.
Because we are not dealing with this in this complete situation, right? So this is easy. If we can see everything from this 16 cells, we don't even bother using any iterative algorithm. We can just use the maximum likelihood estimation to get a closed form and quickly calculate the R estimation, R hat, and the variance of R hat. Is that correct?
Yes.
But in reality, no, we're not that fortunate. So we only got the data like this. Why? Because these 4 categories are confounded by each other. They are merged together. You cannot distinguish one by the other, one another. Do you agree?
Yes.
Yes. So this is the problem. So now we're dealing with this incomplete information situation. This is incomplete, which is the reality. This is the complete. We have to use the EM algorithm to help us to deal with the incomplete data problem. Questions? No question? Okay, let's move forward. Now, EM algorithm, okay? So this is the 9 categories here. So for the category, this one and this one, that's easy, right? We can easily distinguish these 4 categories from the other categories, right? Only this, and this, they are standing out by itself. And especially for this one. So 4 categories are mixed together, so you cannot distinguish one another from this category. Is that correct? So the same here, the 4 subcategory, they are combined to form this single category for this 9 category problem. Is that correct? Okay, good. Remove this. And Okay, now this is the probability associated with each of these 9 categories. So let's give you an example why this is this. So for the first category, it's easy, right? So can anyone tell me how we can calculate this? What is this? So if we go back to this, so this represents this. So why is this? Can anyone tell me?
Because there is a 1/2 multiply 1 minus r.
That's
So it's
right. Yes, because
power.
if you look at this parent and this gamete, so that's the probability to get this gamete. Is that correct? Because 1 minus r represent this is a parental type. There's no crossing over. Then the probability is 1 minus r. And this parent can generate 2 parental gametes, right? Parental type gametes. So that's why the probability of this is 1/2 times this. Is that right? The same thing for this parent. They are identical. They are symmetric, right? So this gamete still 1/2, 1 minus r for this one. So these 2 gametes come together to form this category. So the probability should be the multiplication of these 2. That's this. Is that clear? Okay. So that's why for this category, it's easy to get this, right? The same thing here. So why is this? Can anyone tell me? Why here is 1/4, but this one is 1/2? Because this one has 2 categories here, right? 2 categories.
Mm-hmm.
If you look at here, so the yellow thing, so each of this yellow is 1/4. One gamete is a recombinant, non-parental type, and 1 is the parental type. So this is how we calculate the probability for this category, right? And these 2 are the same. So if you add up these 2, this gives you 1/2 here. So I don't want to spend more time on this. So the same thing here. So you can easily derive this. Is that okay? So yeah, it's not that hard. For this class, it's not that hard, but so it requires us to be very careful and to be patient, to do a lot of like calculation and derivation to make sure everything is correct. And yeah, any questions? Okay, now we have the counts for 9 categories. Okay, and we have the expected frequency for each category. Do you agree? And then we can construct a likelihood, log likelihood function. But this one is based on what? This log likelihood function is based on the incomplete data. So we give a name to this function is a incomplete data log likelihood function. Because it's very hard to use the regular MLE method to get a closed, nice form of solution for the R hat. So that's why we will use the EM algorithm. So right now I'm coming back to Ryan's question. So why we need to use EM here to solve this problem? Because this likelihood function has some incomplete information. We use EM algorithm to deal with this incomplete log likelihood function. Any questions? Okay, so to help us to facilitate our calculations, so we rewrite data into a different way. So we have 9 categories here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. The only problematic category is the number, if it is this category, because the 9th category is a mixture of all these possibilities here. Can you follow me? So this is the problem, where the problem is, and we have to use the EM algorithm to help us to deal with this specific category. Why? Look at here. So what is this? These 2 subcategory. So what do you think? So from the genotype, what can you tell about these two subcategories in this ninth category? These two represent the parental type, right?
Parental.
Yeah. Do you see any crossing over? No. So those are the parental type. So parental type means what? It means 1 minus R times another 1 minus R, right? There's some coefficient ahead. We just ignore those. So this represented the core probability for this, right? The same thing here. Can you follow me? Because both gametes from two parents are parental type. No crossing over. How about this two? So it's easy for us to write the core probability for these two categories like this. Do you agree? All right. And here, so I put category, so I just mentioned that to facilitate this calculation, I use different label. I reclassify these 9 categories into 4 categories. The first category, I use label 0, means, okay, this two, there's 0 crossing over occurring here because all this individual progeny represented the parental type, right? So there's 0 crossing over in each of these categories, subcategories. I labeled 1 here because if you look at each of these 4, there is only one gamete having a single crossing over. The other one, no, parental type. One parental type and one non-parental type, which means all this individual only has 1 crossing over, right? So here, 2 crossing over because 2 gametes are all non-parental type. But 3, no, you cannot use 3 crossing over. So this is a very special case. So here is a combination. Either there's a 0 crossing over or there are 2 crossing overs. So I purposely put them into these 4 categories to facilitate our calculation. So for the first category, we use a new label, new notation for this. I use the N0 here to represent the number of individuals, progenies falling in this category. N1, N2, and N3, because N3 is like 2 parental type plus the 2 non-parental type, right? Okay. Now, so if we assume we can distinguish the individuals in this category, if we assume, so we can easily get a closed form, very nice closed form for MLE, right? Estimation. If we knew these numbers, if we have the complete data sets, we can easily, if we knew this realize the numbers, if we are dealing with the complete data problem, so we can easily get a MLE for this estimation. Do you agree? Okay. So if we knew these numbers, so in reality, these 2 numbers are mixed together, so we cannot distinguish these 2 numbers, right? But if we knew these 2 numbers, then we can easily get the MLE for this estimation. So this is the MLE. Why is that? Because this is the total number of the individual is N, and we multiply this number by 2 means like how many gametes we can get from this N individuals, right? This is the total number of gametes, and the numerator represents the gametes that carrying crossing overs. So do you agree? So if you look at here, so the numerator represents the number of gametes carrying a single crossing over. So if you see 2 means like both gametes carry a crossing over, right?
Mhm.
Any problems here? Any problems? So this is, yeah, go ahead.
So n is obviously number of progeny. 2 is number of gametes.
Yeah.
So we subtract that from the numbers that we do know, then we get the number of gametes that are in the empty space that we don't know.
Yeah, yes, that's right. So let me describe this. So suppose we knew these numbers, okay? Oops. So here we try to estimate this, right?
Mhm.
The recommendation frequency. So we knew if we have the full data, the complete data, we can get the MLE, which is the total number of gametes, and among this total number of gametes, what is the number of gametes carrying a crossing over? Is that correct? So this is the MLE, right?
Mhm.
And if we rewrite this, so this is equal to this. Why is that? Because this is n is the total number of individuals here. So look at here. So this is n, right? So this is the total individual you get from this experiment, the
Yep.
progeny.
Mhm.
And each progeny has 2 gametes. So that's why we multiply this 2 by this n. So this 2n represents the total gametes we got from this experiment, F2 experiment. Do you agree?
Yep.
Now if we want to calculate the R, so we need to construct a ratio like this. So the numerator represents, out of this 2n gametes, how many gametes have a crossing over on it? Is that right?
Mhm.
So the N1 means what? N1 here means the number of individual that carrying only one non-parental gamete. Do you agree?
Yes.
So that's why we put the N1 here, because for this individual, they only carry one recombinant gamete and one parental type. So only N1 gametes are having a crossover, right? So that's why we put the N1. But in these categories are different because in each of these individual, they carry 2 recombinant gametes. Do you agree?
Mhm.
So that's why we put a 2 here. Does that make sense?
Yes.
So if we add up all these numbers together, that means like out of this 2n, how many gametes have a crossing over on it? So using this is MLE actually. So this is MLE. We use this. If you do the maximum likelihood estimation to get the first derivative and the second derivative, this is the closed form. This is the solution that MLE can give you. Makes sense, which makes sense, right? Intuitively.
Mhm.
However, yeah. So the reality is always like frustrating. So we don't know these 2 numbers. So we cannot get the real solution for this problem because these 2 numbers are not observable. So that's why we're going to use EM algorithm to help us. Okay, so in the EM algorithm, so we're going to calculate, instead of use the realized numbers here, these 2 numbers, we use an expectation step to replace this. Then we can construct a iterative algorithm to help us to get the solution, best solution. Any questions?
Nope.
Okay, very good. All right. So, okay, now, so the EM is mainly focused on this category, right? Because this category is so miserable because this one consists of 2 categories, 0 recombinants and the 2 recombinants. So we use EM algorithm to specifically deal with this category. So remember from this slides, we want to calculate the expectation for these 2 numbers, right? So this is the major part. So now we want to calculate the expectation of this. suppose we already knew at time t, so at time t, the current, suppose we have a value, realized the value for this R. So how can we get the expectation value for this two? So first, let me know. So can you tell me what are these two numbers here? What are these two numbers?
Those are the values that we do not know.
Yes, but we do not know these four numbers, right?
Yes, we don't know
So
those.
how about these two numbers? So these two numbers represent what?
Half of the values that we don't know.
Yes. Okay. So these two categories, yeah, I think, yeah. So maybe I'm asking, not, yes.
Non-parental.
Yes, these
Oh.
are the non-parental. So these
Okay,
two
yeah.
numbers represent the progeny carrying two
Two.
non-parental gametes.
Yes.
And these two actually represent the progeny carrying two parental gametes. Is that right?
Yeah.
Mhm.
So because we want to differentiate these two categories within this M22 category, right? This is the total number we observed for this category. Is that correct?
Yeah.
But we don't know among this M22, how many are this category and how many are this category, right? This is what we want to calculate, right?
Mhm.
Am I clear?
Mhm.
Okay, now if we knew this number, so this number is observable, so this is the data we have, right? And if we knew the R value, the realized R value for R at time t, so can we use this to calculate the expectation of this two? Yes, we can, because this represent the recombination part, and this represent the parental type, right? And the sum represented the total of this M22. And this part represent only the non-parental type. So the ratio of this actually represent the ratio of non-parental type out of this many individuals.
Mhm.
Is that clear?
Yes.
What is the time t?
Time t, for example, so R time t means like, so we do the iteration. So at any time, you have a realized value for R, right? For example, at time 0, you don't know. So you give the program an initial value like R0 equals to 0.2 or something. So the current time R0, R equals to 0.2. And if you start the iteration, at any time point, you have a realized value for T. You have
Okay.
at any time of t, you have a realized value for R. Is that correct?
Yeah.
Okay, so that's the thing. So at time t, you can have a realized value for R, and you use this formula to calculate the expectation for this category, which is equal to this, and then you use this into this formula. So this formula on the right hand side is a function of R time t, but you use R at time t to express R for time t plus 1. So you can update the R based on the new data. Do you? Okay, let me explain this again. So this is important. This is the core idea about this iterative algorithm. So I would rather to spend a little bit more time on this. Okay. Oops. So do you have any problem with this?
Nope.
Okay, good. So suppose at time t, let's do this. Okay. So this is the R estimation, and this is the time. Okay. So at time t, we don't know R, but we can. So let's say this is 0 and this is 1. So and this is 0.5. So at time t, we don't know R value, but we can initialize this value. Let's give a 0.2 to this R0. Can we?
Mhm.
Okay, now this becomes R0, okay? R0.
So R0, maybe it's a random value, or
Yeah.
we just set it.
Yeah, R0, so starting value. So whenever you do any iterative algorithm, so you have to give the program some initial value. So this is the R0. Okay, but reasonable, you cannot give R equals to 0.8. So that's a problem, okay?
Yeah.
Give them, usually get the best guess for the R0 and give it to the program, and the program can update this value iteratively. So, okay, now we have R0, because if we assume R equals to this, right? Then can we calculate the expectation value for this too, based on this, right? No problem, right? Okay, now once we have this represents the information at time t, right? Time 0. So we plug this information here. And this is, this is the next time point. So one time equals to 1. So we can update this R, maybe starting from 0.2. So the next one is 0.21. When you update this one, so you calculate the t of the next time point, t equals 1. So you may end up with R equals to 0.21 here. It's a little bit different from your starting value, right? You use, so here, R0 equals to 0.2, am I right? And you use this information to plug into this. This is MLE. This is the maximization step. This is the expectation step. This is the maximization step here, because this is MLE. If you use this value to plug in here, you can calculate R t plus 1. Can we? All right, so suppose after the calculation, the R, now R1 equals to 0.21. Suppose it's here, right? Then we go back. We go back here. So we start from expectation step, and then we migrate into the M step, and then we go back to the E step again. We use the R1 here to calculate this expectation and use this to plug this back again, go back to M step again, calculate R2. So you're gonna see a trace like this. Is that clear? So this represented the converge. Any questions? So what do you see here? So here we use we use the EM algorithm. So we have two major steps, right? The E step and the M step. So two steps are alternated in an iterative way. And so in this way, the only thing we need to do is to initialize this parameter. We give the parameter a initial value, reasonable in a reasonable range, and we let the program to run by itself, because we have the clear form, the closed form for this MLE. Because if we assume this is a complete data problem, so we can get a very beautiful closed form for the MLE, right? But the problem is like, there's a missing value, there's a incomplete data. So we use the expectation step to get this, to get the expected value for this missing data. And we use this expected value for this missing data and plug this value back to the maximum step, maximization step. And we alternate, so these two steps are alternated in a iterative way until the entire program converge. Then you get your solution. The same thing. Is that clear? So any questions? Yeah. This is very important because at this in the first few lectures, I try to slow down because those are very, very important and hard theorems. Once you get these ideas, get this, so get it right. So in the future, when we apply these theorems to different situations, that'd be very quick. So we will go very fast. So any questions so far? So we're almost done with this chapter.
I have a question.
Yes, please.
So how do we decide on the first R at T0? How do we decide this would be the value?
Oh, you
Yeah.
mean the 0, right? Okay, so you mean here? How
Yes.
do we decide the initial value for 0 for R0?
Yep.
Okay, so we don't know. So each one, so each person may have like different idea. So, but if as long as you give the R0, the initial value, a legal value,
Mhm.
what is the legal value or the reasonable value? Because we knew what we are doing here, right? So we want to estimate this R. So this R is the recombination frequency. And we knew this R should be any value between 0
0 to
and
0.5.
0.5. So this is the legal range we can choose for assigning a initial value to the R0. So different people may have different idea. Maybe for me, I will give a value in the middle, like this. Yeah, to R0. But if you have some prior knowledge, because so for example, if you knew these two loci should be very close to each other, so then you can give a smaller value. So for example, you can start from 0.1.
Mm-hmm.
But if for some other experiment, you have some prior knowledge, okay, these two loci maybe not that tightly linked. So you can give it a initial value like 0.4. So it's totally up to you.
Oh, okay.
But usually the program is very robust. So no matter what value you give to the initial value, it can quickly converge to the real value. So it's very robust.
Mm-hmm. Thank you.
Sure.
I have a question.
Mhm.
So I understand the value for W, but in the final line of equations, we have M22, M13, M31, M1, and then we have another parentheses of M12, M21, M23. What are these two categories?
Oh, yes. Okay. So start from here. So this is what we get, right? So if we go to the previous slides, so this is what the MLE tell us, right? And we need to plug in the expectation for this too, right?
Mm-hmm.
So you understand this part, right? And this is the same for that part.
So we're
Correct.
including the expectation value into our
Yes. So you basically you need to
R
use
equals
this
T plus 1.
plug in here. Yeah. So this represent, I believe, represent this too. So if you go
Okay.
back, yeah, N2 represent, yeah, this too.
Okay, it's an equation expansion.
Yes, and this is N1, I think. Yes,
Thank you.
sure.
That's all I needed to know.
Mhm.
Now I can start putting it together.
Very good, very good. So any questions? Yeah, we are in very good shape, I think. Yeah, it's cool. All right, so if you do not have any questions, I'm gonna finish this and we're gonna continue for the next chapter. Is that okay? Okay, let's start from, well, it's the other one. Give me a second. Close this one and open this one. Okay, perfect. All right, genetic mapping construction. All right, so what have we learned so far for the first two chapters?
How to estimate the recombination fraction.
Yes. Yes. So the first chapter we learned about the map functions, right? And different versions of that, and how we link. We use the we use the map function to find an association between the x, which is the additive measure of the map distance, with the non-additive, which is r, right? The recombination frequency. But in reality, we use r very often to measure the genetic distance between two loci. And in chapter 2, so we use all kinds of like the advanced statistical method to help us to estimate this r, the magical r, right? Using two basic important fundamental designs. We use backcross design, or we can use better F2 design to get more data. Using the progeny data, we can use that data to help us to estimate this R, right? R hat, using different ways. MLE, if we have the complete data, so we can easily use the MLE to get the R hat. But sometimes, like when we do the F2 design or other design, so we have some missing data or the incomplete data. So we cannot easily use MLE to get the estimation. Then we can apply some advanced method, for example, Newton, Raphson, or Fisher scoring method, or EM algorithm to help us to get the estimation. So now, chapter 3, once we can easily estimate the R value for two loci, can we study the arrangement for more than can we study the arrangement of more than two loci along the chromosome? Yes, we can, right? Since we can calculate the R, the genetic distance between any two loci, so we can put more loci. We can put more than two loci in a correct order along the chromosome. So this is what we're going to do in this chapter. We're going to create the genetic maps for more than two loci using the knowledge, using what we have learned in the previous two chapters. All right. Okay, let me see. What time is it now? Okay, so yeah, we're doing good. So today I'm gonna stop the lecture around 11 o'clock. So I think yeah, we are doing good. And I'm gonna. So if you have more questions after the class, so we can stay longer. So I can help you to answer questions. So far we have 10 minutes. Let's cover a little bit more about the chapter 3. All right, so suppose this is the chromosome and we are starting on 3 loci now. So we have loci A, loci B, locus A, locus B, and locus C. Suppose the correct order is like this. So if they are located on the same chromosome like this. So how can we use what we have learned so far to identify this right order? So this is what we want to do now. Okay, suppose this is the right order, ABC. But if you do not know the right order, so you can think maybe these 3 genes or 3 loci are arranged in this way, right? So how you can use the information R, the estimated R value to help us to put the 3 loci in the right order. So first thing we can use is this thing. So we can use the sum of adjacent recombination coefficient. In short, SAR, SAR. So SAR is defined in this way. Okay, the adjacent recombination coefficient like this. So how do we do this? For example, if we want to calculate the SAR of ABC, this order, so the B, suppose B, if the order, in this order, if B is in the middle, so the SAR ABC should be the recombination frequency between A and B plus the recombination frequency between B and C. So this is the definition. If we want to calculate the SAR for this order, ACB, C is in the middle, the same thing. So we can add up these two recombination frequency, RAC and RCB actually. Is that clear? So this is the definition. So we want to calculate these two and compare SAR ABC versus the SAR ACB to see which one is greater. Because based on our theorem, so we will find the right order based on the minimum value of this SAR value. So we can compare these two and find the smaller one, and that smaller one gives you the right order of these three loci along this chromosome. Is that clear? So we're gonna prove why this is true. Why this is true. So suppose, yeah, this is the right order. And if this is the right order, so the SAR of ABC should be the smallest one. In other words, if you calculate different order, so we can calculate the SAR, ACB, C in the middle, or we can also calculate the SAR, B, A, C, A in the middle, right? So we can calculate these three things. And because the right order is this, ABC, the B is in the middle. So this SAR value is always less than this two. So we're gonna prove why this is true, okay? So the true order is this. So the SAR, this is not SAR, this is actually the recombination frequency between A and C. So we have covered this before, right? When we talk about the genetic map, the calculation, because R is not an additive measure of the genetic map. If we knew RAB and RBC, so if we want to calculate RAC, so it should be equal to this, right? This is what we have learned before. All right, this is the reality. All right, now let's calculate SAR ACB. SAR ACB based on the definition should be equal to RAC plus RBC. Any problem here? Any questions here? This is by definition. So if we want to calculate the SAR ACB, so that's the definition. And now we can substitute this thing by this, okay? Then we can rewrite this SAR ACB equals to RAB plus RBC minus this. This is RAC, right? The whole thing. Plus this. Is that correct? And if you do a little bit like rearrangement, so it will give you this plus this, okay? And what is SAR ABC? So this is the SAR ABC, right? They are the same. And the SAR ACB, actually there's an extra term here. So if we want to see which one is bigger, so we only need to see if this one is positive or negative, right? Okay, so can anyone give me any idea about this value? Is this positive or negative?
Positive?
Yeah, positive, because we have a boundary for R, right? Any R should be less than 0.5. So this thing should be less than 1, and 1 minus this thing should be a positive thing. And R itself is a positive thing, so the whole thing should be a positive thing. So which means the SAR ACB should be always not less than SAR ABC, right? So yeah, this is a beautiful proof about why we can use the SAR calculation to help us to find the right order of ABC if we knew the recombination frequency.
Just a quick reminder, SAR ABC needs to be a value of less than the other two combinations.
Yes.
Got it.
Yes. So this is not difficult, right? So Probably, yeah, it's very likely that I'm gonna give you something similar in the final exam to prove something like this. So if you have like the recombination frequency estimated for each pair of loci, so how do you prove? Just show me the SAR value calculated from the right order will be the minimum one. Is that easy?
I do not follow that.
I'm sorry?
I did not follow that.
Okay, let's do this again. Don't worry.
I just didn't follow the last sentence you said
Okay, sure. Last sentence about here, right?
about the question you would be postulating on the test.
Oh, sure. So this slide, so on this slide, I just show you why. So suppose you have, suppose the right order of ABC is like this. So you can calculate three things, right? The SAR ABC, the SAR BAC, the SAR ACB. Is that correct?
Hmm.
Yeah, because if you do not know the right order, there are three possible orders, right? So because we have three letters here, so each letter could be located in the middle. So then you have three possible orders. So now if you have the information, if you have the data from which you can calculate the recombination frequency for each pair of these two letters. Suppose you can calculate the RAB, RBC, and RAC. So how you use this number to help you identify the right order? So what you can do is like, you can calculate the three values here: SAR ABC, SAR ACB, SAR BAC, right? And find the minimum one. The minimum one will give you the right order. So this slide actually shows why the minimum SAR value will give you the right order. Suppose this is the right order, and we know this part, right? So if we knew the recombination frequency between A and B, and between B and C, so this is what we have learned in the first chapter. So how can we use this to calculate the recombination frequency between A and C? So this is how we do this. RAC equals to RAB plus RBC minus these two things. This thing, right? Can you follow me?
Yep.
Okay. Now let's calculate the SAR ACB first. So by definition, RACB equals to this plus this. Is that right?
Yep.
Adjacent.
Mm-hmm.
So this is the definition actually. If you assume, if you want to test this order, so A, C, if you want to test this order, so you need to calculate the SAR value for this order. So this order, there are two adjacent R value, which is RAC and RCB, right? RBC. Is that correct? And then you just add up this two. By definition, this is the SAR value. And okay, now this thing can be replaced by this because of this. And after the rearrangement, you get this. So this is the value for the SAR ACB. Now you want to compare this SAR value ACB versus the SAR ABC. We want to approve this is smaller than this. This is bigger than this. Bigger or equal than this. So this is what we want to prove, right? Okay, so this by definition, this is how we calculate the SAR value for ABC. Because if you want to evaluate the order of A, B, and C, so this is how we define this SAR value equals to RAB plus RBC here. Okay, now this is this. And if you compare this two, this part are identical. So we only worry about this part. If this thing is a positive one, then this thing is bigger than this, right? If this is a negative thing, so the other way. So based on our parallelism, so this R is a positive thing and less than 0.5. So the whole thing should be a positive thing. So which means this is greater or equal, at least not less than this value. Am I clear?
Mm-hmm.
So we proved if ABC is the right order, then if you calculate the SAR value of ABC, this should be the minimum one compared to the SAR ACB and or SAR BAC. Is that clear?
Yes.
Okay, very good. So, okay, so since we can use the SAR, which is the sum of the adjacent recombination frequency coefficient, so which is R, we can also use X. What is X here?
Number of crossovers.
Active.
Yes, this is the additive measure. We can also use this criteria to find the right order, right? If we knew the X rather than the R, we can use the same theorem to find the right order based on the minimum sum of the adjacent genetic distance in X in additive measure. Any problems here? So we can move forward just like fly. Yeah, very, very quickly.
What is X hat?
Yeah.
What is
Go
it
ahead.
again? What is its name?
You mean this one?
X hat, yes. What's its name again?
I think the sum of the adjacent distance, I guess. So I forgot the real name. So for this one, SAR means because sum of the adjacent recombination frequency. That's why we use SAR, right?
Mm-hmm.
Yeah. And so if you go back to the text, so probably you can find the right name. So this should be sum of adjacent distance or something like this. So this is, I'm sorry, what is that?
So it's like the real distance in the chromosome?
Yes, something like that.
Something like
So this X actually represented the average crossing overs between.
over, yeah.
Yeah.
The crossing over
Additive.
numbers, yeah.
Yeah, numbers, yes. You can also use this, and also you can use the likelihood as well. So you know how to construct the likelihood, right? So we have learned this before. But in this way, we need to find the maximum value because the likelihood is different from the distance. The distance, the SAR, the sum of the adjacent R recombination frequency coefficient gives you the right order with the minimum number of that SAR value, right? But if you want to use the likelihood value as a criteria to find the right order, so you always find the maximum of the SAL value. Does that make sense? The distance, if you use distance to help you identify the right order of ABC, so you always find the minimum value of this SAR value, because the right order will give you the shortest that thing, right? The smallest that thing. But if you use likelihood value rather than the recombination frequency or the additive measure X, then the criteria change. That you need to find the maximum value to give you the right order. No? Doesn't make sense? Because the recombination frequency will give you the best solution for the order because it will give you the shortest distance, right? But the same R will give you the maximum likelihood, the likelihood of the maximum value. So if you use the likelihood value, so this will give you the maximum sum of this value. Does that make sense? Okay, so I'm gonna stop here. So I think, yeah, probably today I have taught too much stuff. So I think you need time to digest. So any questions for today?
Why are these why are these values interchangeable within the equation?
Oh, okay. That's they are exchangeable by definition. Let me show you. Why is that? You mean here, right?
Yes.
Oops. Okay, let me remove this first. Okay. So probably there's some confusion about these definitions. So let me help you clear those confusions. All right. So in the first chapter, so when we calculate, so in the first chapter we learned how we calculate the recombination frequency between A and C using recombination frequency between A and B and B and C. So do you still remember this function, this formula? This is correct, right? So this is totally irrelevant with this. So this is a new definition now. So what is this definition? This definition is here. So suppose you want to evaluate a specific order, either ABC or either ACB. So by definition, the SAR equals to, so for example, if you want to evaluate this order, the SAR becomes what? Becomes the sum of the recombination frequency between these two adjacent letters, which is RAB, right?
Mm-hmm.
And this two, RBC. So this is your SAR A, B, C by definition. Okay, is that clear?
Okay. So
now,
then,
if you want to evaluate this order, go ahead, Ryan.
Then that means that the equation where you change it with x hat, or the likelihood equation, it's the sum of adjacent map distances, the sum of adjacent likelihoods.
That's right. Yes. So you can use different things to help you, but this R is the simplest way, but yeah, so yeah, usually we would like to use the simplest way, but I just want to teach you, like, there's a multiple ways you can use to help you do this mapping. All right, to find out the right order of ABC. Okay, so suppose you want to evaluate this order because you don't know which one is correct, right? So you can do the same thing to calculate the SAR for this order as well. So if the order you want to evaluate is this, right?
Yep.
So this means like you need to add up these two things adjacent if you want to evaluate this order. So this becomes what? RAC plus RBC, right?
Mm-hmm.
Okay, intuitively, so because now you have like, so let's do this, RAB plus RBC, is that right? This is by definition, right? Now you want to compare this thing with this thing to see which one is smaller, because the smaller one will give you the right order, right? So intuitively, if you compare these two, so this is the same with this part. Only this part is different from this part. Is that right? If the right order is ABC, of course, RAC is greater than RAB. So this one will give you a smaller value. Is that right? So, but we cannot say this. So we have to prove this. So that's why we use this. We use this. We use this things to help us to prove why the right order, the SAR value of the right order will give you the minimum value of that thing. Is that clear?
Mm-hmm.
Mm-hmm. Very good.
This is just a game of finding which one's greater or lesser, RAB or RAC.
That's right. That's right. So this is very important. It's not that hard. So it's reasonable for me to put some questions like this on the final exam. So I'm going to ask you to prove something like this for me. Is that reasonable? Okay. Any other questions?
Yeah, I have a question. Can you hear me?
No. Okay.
Yeah. Like I have two questions. My first question is,
Yes.
so why do we design or use the SAR or the?
Why? I'm sorry. Could you say
Why
that again?
do we like define the SAR? Because like in my understanding, if the 2 points has the largest recombination coefficients, so they are on the two end. So
Yeah. So good question. So because we're only dealing with 3 loci, so in the future, when we deal with like 10 loci, so there's all kind of combinations of this order. So you have to use some criteria to help you to quickly find the right order, right? For 3, it's easy. You just, if you have 3 R values, you can find the biggest one, and this will give you the optimal order of ABC, right? So if you think about like, if you want to extend this problem to 10 loci, it's not that easy for you to find the right order for the 10 loci. So you have to extend this SAR calculation for the 10 loci to find the optimal order of the 10 loci. Yeah, this is a good question. So for this 3 loci, it's easy for us to identify the right order even without this SAR value. I agree. But I just want to show you this is the principle behind. So when we deal with more than 3 loci, so this is super useful.
Okay. And the second question for the SAL, and is about the sum of the likelihood. So, but for the R hat, for example, if we use the maximum likelihood estimation to estimate the R hat, and then we will put the R hat into the likelihood function.
Yes.
Right. Is that
that's the same. But
so that means
you mean this, right?
Yeah. And so this function means we will like compute the value of the maximum of the likelihood and sum them together, right? So yes. Is there any like proof to because it's related to the like your experiment? How do I say that? Like, is there any proof to like show
any
this?
Proof of this? Oh, okay. Yes. So first, I will not ask you to prove this for me on the final exam, but yeah, I think we can prove this because let me think. Okay, I think this is a very good thought.
Because like in my understanding, like for the first 2 is very obviously if a BR on the end and the RAB should be the largest, or the AC should be the largest. But for the likelihood part, I'm not pretty sure if AC are on the 2 ends, their maximum value of the likelihood should be the largest.
Sure, let's do this. Okay, so suppose this is the right order. So we want to calculate the SLL, do we? So we want to calculate this value. Okay, now suppose we can get the likelihood for RAB. Okay?
Yes.
And then we can get the likelihood for BC. Right?
Yeah, RBC.
And we can also get the likelihood
AC.
For AC. Okay. So we want to evaluate whether this one, ABC, is bigger or ACB is bigger, right?
Yeah.
So based on definition, okay, let's see what is this. So this is the likelihood of AB plus likelihood of BC, right? R, sorry,
Yeah.
okay. And this should be likelihood of AC, RAC. Plus
R
likelihood of
CB.
RBC,
Oh.
right?
Yes.
Okay. Now you mean, so it's not that straightforward that this will be greater than this, right?
Yeah.
Okay, let's do
Cause
the proof. Okay, so based on your so here, suppose we also have a experiment, let's say backcross, and we generate like 1,000 progeny. Okay, so we can easily calculate either the likelihood function or the, oops, let me see. Okay, so for this too, so
yeah, same.
this one should be okay, right? Should be the
Yeah.
same. But this one and this one, we want to calculate whether the likelihood of R, A, B estimate is
Small.
greater than the likelihood of R, A, C. Yes.
Smaller than LRAC.
Hmm?
But it's in.
You mean this?
I think it should be smaller. Like if the order is ABC, the LR
The first
AB
is
hat
LR,
should
AB,
smaller than.
This is AC. And let me think. All right. So the problem is this. So this, I think this is very, this is a good question, but I would argue like this. So, okay, because this is shorter than this, right? AB is shorter than AC.
Yes.
Am I correct? Am I
Yeah.
correct?
Yes. But if AB is shorter than AC,
Okay.
we can prove RAB it should be smaller than RAC.
No, this is likelihood. This is not R. This is likelihood.
Yeah. I mean,
Okay, likelihood means what? So you need to find the best estimation for this, and this will maximize this your likelihood. Is that correct? This is what we do for the MLE, right?
yeah, yes.
Okay.
That's correct.
I think your question is like why we can prove this likelihood is greater than this. I can give you some argument. So although I didn't read this part. I think probably in the textbook, Dr. Xu mentioned this part, but I read that part, but I forgot. But I can give you based on my own understanding. So this is true. The likelihood of RAB hat is greater than the likelihood of RAC hat. Why is that? Because so if the real order is ABC, right? So the distance between A and B should be less than the distance between A and C. Is that correct? So
Yes.
All right. So the chance of having double crossing over between A and C is the chance of probability. Let's talk about double crossover between A and C should be greater than the chance of the double crossover between A and B. Do you agree?
Yeah.
Okay, then if you only look at the AB or AC and use the recombinance, using the recombinance progeny divided by the total progeny to calculate the R hat recombination frequency. So which one will give you better estimation of the R?
Which one?
Because AC is larger, so the chance of having double crossing over is much higher than the chance for AB, right?
Yes.
So the double crossing over, actually, you cannot see the recombinant. So you incorrectly remove those progeny from your calculation. So actually, you should count 2 for those double crossing over, but because you do not see the recombination from your progeny, so you underestimate the R. So that means like your R estimation is less accurate than the RAB. The estimation of RAC is less accurate than the estimation for the RAB, right? Then if you use a less accurate estimation to calculate the likelihood function, so it will give you non-optimal likelihood. So in this case, the likelihood of RAB hat should be greater than the likelihood of RAC hat. I'm not sure if I make it clear.
Yeah, I understand the meaning.
Mm-hmm.
What do you mean? Yeah.
So is this your question? Was this your question?
Yeah.
Okay.
Like I just want to like ask if there any like improvement for this part. But I'll check the Dr. Xu's book.
I will read it again too. So I think I
part.
read about this, or maybe he didn't mention about this. He just talked about like maybe we can use this as well as a criteria to figure out the right order of ABC. But this is a very good question. So I think there's a lot of like important biological theorem behind your question. So good one.
Thank you.
Sure. So any other questions?
That was fun to go over.
I'm sorry?
That was fun to go over.
All right, so let's see. Okay, so I think, yeah, we are in very good shape. So as I mentioned, so at the beginning, I tried to slow down a little bit to make sure everybody can follow those important theorems. And in the future, when we feel very comfortable about all these theorems, we can move very fast. Okay. All right, so if you do not have questions, we're gonna stop here today and see you on Thursday. All right, have a good one, bye-bye.
Thank you. Bye.
Thank you, bye-bye.